Alrighty, then we continue on this one. So there we have an example. Ooh, 4 watts. Oh, this is a home exercise. Excellent, even better. So this is for you for home exercise to do this design of the amplifier. And if I was Javi, I would put this one as an excellent question on exam. Design an amplifier with, of course, the different values. Yeah, that well, but I'm evil. I'm not sure if Javi is that evil. Although we are both dinosaurs, and we eat students, you know. Yeah, carnivorous dinosaurs. Okay, example. Okay. I think that's the next one. So average and instantaneous dissipation. So now we have this high frequency signal. So basically, high signal meaning high frequency signal meaning that the this device does not heat up. Or basically, when you think of a heating curve, when you have the, well, for example, AB class amplifier, where you have the power, instantaneous power in transistor, it's basically, well, you have I2, follows the IC squared signal, like that. That's the instantaneous power, the power on amplifier transistor. Okay, it looks like that. So that's basically that. I2 square I alt or IC squared divided by RL. Something like that, yes. Instantaneous power. Okay, for high frequency signals, it means, okay, if you start, well, that's the average power here, somewhere in here. Average, PDQ, average, okay. So in average, this actually the heating part. So fundamentally, when you have power on here, you start heating the amplifier or the transistor. So basically here you are heating the amplifier. Well, let's see, how does it go? It goes, heating goes something like that, I think. Okay, until here you don't heat it anymore, okay? So that's the temperature to amplifier, and then it starts cooling down like that, and then it starts heating up again like that. But in average, this would be basically based on the thermal capacity and the thermal capacity and actually the thermal resistance to the heating, the cooling element. Okay. So the temperature here follows that one. So if you have a, well, this would be in between low and high frequency signal. You really start heating it up more on the on that cycle. But if you have really fast signal, then basically this becomes, you know, just like that. It's in average, it heats up at that rate. But for slow signal, actually, it starts also heating the transistor more on this on duty cycle. Okay. So basically, you need to go. So basically, you need to go on slow signal or very slow signals to do the instantaneous power calculations. And for AB class amplifier, the maximum instantaneous power in transistor is found on the middle of its load line. Yes, that's actually we found out. And then basically we have the PD in the max on steady state happens in, well, the maximum constant current, and that becomes half of the maximum on the load. So 100 watts amplifier now requires 50 watts the design for the transistor. Quite big difference compared to 20 watts. The sinusoidal, you are dissipating 20 watts on this kind of steady state. On the fasting nodes, in maximum it dissipates that 20 watts. But here we are dissipating basically 50 watts. You need to take care of that one. Okay, yeah, which happens to be much higher than what we able to the average power. Oh, yeah, I remember it wrong. It's actually 13.5. Okay, much higher. So it needs some engineering factor. And now you know where the engineering factor comes from. That's one design consideration. All right. Thermal feedback is very dangerous effect on AB class amplifiers. And even more dangerous, this is now the bipolar transistors, but if you actually have a MOSFET output stage, then it becomes even more dangerous. When MOSFET burns, it burns always on open, on short circuit. So it becomes conductive all the time. So it means that you blow the output stage, you blow also the most probably power supply, and you fuse on your circuit breaker. So a lot of bad things happen, and even on this, if you get into bad thermal feedback case in class AB, then you can also start blowing fuses. Not only your own, but also the real fuses. Okay. Where that actually comes from is explained on this. So we are first of all we are starting to generate heat on the transistors, which means that we are also with the same bias voltage, we are biasing actually since there's that small, okay, that explains it all. So we have this small current coming here, but when the temperature rises, we are also shifting collector, the bias current, higher. Okay, and now actually you can end up in the situation, well, that here generates more heat when you have more current on collector. It generates heat and more and more and more, and finally it says poof. You know what is the principle of electronics, where it actually gets all the the magic that make electronics works. All electronics is included with some internal smoke. So if you let the smoke out, it doesn't work anymore, right? So keep the smoke inside of the circuits. Yeah. And yes, it can actually end up blowing up the transistor. And yes, we need to include protection elements to avoid the destructive effect. Okay, one protection element actually would be to have a fuse on. somewhere in between the power supply. Well, there's always one fuse between the power supply and the outlet, AC outlet. And then there should be also one fuse inside of the inside of your amplifier. And basically, I would put there a thermal fuse next to the amplifier circuit. So the thermal fuse blows off before this basically the thermal destruction would happen. So that's why those thermal fuses are there. You put one there and cut the power from the circuit. Since basically the fundamental problem here is that when you get into the bad case of thermal feedback, you don't need any signal anymore, and this is still rising the temperature. Okay, it gets unstable. All right, so thermal escape. Yeah, protection. Okay, and then there we have very simple way of reducing. Well, we not necessarily eliminate the effect, but actually, if you put a couple of these small resistors on the emitter, then the effect is actually about the same as a standard voltage follower kind of case. So that one puts a limit for IC rise. So basically, you are not rising the current because you have there the base emitter voltage plus the voltage drop over that small resistor. Okay. So that actually reduces the effect of thermal escape. Okay, but of course, then we are also losing some power on those resistors. Yeah, but it's a small price. It's a small price. It's a quite small price to pay for a not destroying your amplifier status. Okay, so yeah, and that's basically a negative feedback effect. So if we have a current on collector rising, which raises the transistor temperature, which rises also the collector current, but then we actually have also the voltage drop over the resistor. So it means basically it stabilizes the current so that it doesn't go haywire. Otherwise, think of without that one, where you have think of this circuit. Minus VCC plus VCC. Basically, if you run this one high, and also that drop, if you start rising, well, you can get both of those transistors into saturation if you individually drive those. So it will short circuit between this and that. There's bound to be some smoke coming out of the system. Okay. All right. So, but anyways, that's an easy way to solve the problem. Um, hmm. I have no idea what is going on this picture. Sorry. Oh, okay. Oh, okay. Okay. So we have covered that one more or less, and you can fix it next week. Oh my! Then we have Darlington. Have you covered the Darlington connections yet? Okay, good. Good. So this is basically sort of using the Darlington connection to do basically about the same thing. So fundamentally, what happens is if you're doing it this way, you are well on Darlington you usually just run the emitter as to another emitter, but now we have a different kind of situation. You are basically reversing those, and you are drawing the Q3 actually starts drawing the base current out of the Q1 in if the current goes too high on that transistor. All right, so that's a protective element there. So normally when we don't have any problems, this just runs as normal, but if you are starting to get too high of currents here, then this actually, this transistor opens up and takes some of that. Okay, that was Q1. So some of that, if you have the IB here, you're starting to draw some of that IB down this way. So it reduces the amount of current flowing through the Q1. So that actually protects Q1 to be in thermal. Yeah, the same thing also in PNP. Okay, that's smart. Requires a couple of more transistors, but well, transistors are cheap. And think of now with these transistors, we are actually just taking some of that base current, not the collector current, but base current, which is small, just milliamp or max 100 milliamps of current. So small signal transistor can be here. That's a power transistor. Okay. So, easy solution to build power amplifiers. Huh. Okay, yeah. Two alternatives. Power amplifier with fixed gain, which is specific for application. Okay, or I think on the laboratories you are using that approach. So you have power operational amplifier. So that's basically just a power operational amplifier, which works as ordinary amplifier. It's integrated with high power output states. So those power operational amplifiers actually they are much easier to use than to make your own design. The small thing is about this power operational amplifier actually is that they At least they tend to be, say, quite expensive. But nowadays you can find, say, up to tens of watts with quite decent price. When you go over 100 watts, there are not too many operational amplifiers that can do that one, or power operational amplifiers. But then you actually, when you go over the 100 watts linear, then basically you would do probably driving this high power amplifier state, which is AB class transistor design, with a lower power operational amplifier to make sure that these transistors get enough of base current. Or then, of course, the another one would be to drive MOSFET states and blow few fuses from the house. Okay. So, but anyways, whatever you do, when you're dealing with power, use heat sinks. Use heat sinks. Take the advice from the device manufacturer, what kind of heat sink they actually are recommending on which power they are designed. So there usually are some recommendations what should be the minimum thermal conductivity or maximum thermal resistivity of the heat sink. Okay. When we are dealing with the linear power supply, linear amplifiers, then we really did this. Well, for 100 watts, you can easily end up having a design that you need to actually, in some cases, dissipate at 50 watts on the output stage. That's a lot of heat. Okay, so heat sinks. I didn't see any heat sink on your design. hopefully, you are not running big power there. They need it or not. Okay, good. And then on the laboratory, you will see if the calculus is right or not. Mm-hmm. Yeah, yeah. If it doesn't get hot, then there's something wrong with your amplifier. Yeah, it doesn't amplify. It's bound to be hot. Oh, wow, example. Oh, yes, that's one of my favorites. Is this what you're using on the design? No. Oh, okay, okay. It's also driver state, and you linearize it with the amplifier. With yeah. Feedback. Yes, good. So that's one. Well, I saw you have the output stage, which is in this kind of case. So instead of that output case and your driving operational amplifier, you could have just only this one circuit, and couple of capacitors, input signal tied to the ground, and I would also include here also a for the design if this is okay, it doesn't say anything about if it's audio or not. No, it's okay. This can be used on more than audio, so it has a wide power bandwidth of 70 kilohertz. So you can run the some ultrasonics with this one on lower frequency ultrasonic. Okay. Excellent. But anyways, that's a power amplifier in a one can power supply minus power supply, and then you have this differential input as in any operational amplifier, and then an output. And yeah, see, that's a way to do it. And then we also have this funny, at least for my eyes, that looks funny that there's 1 ohm resistor with the capacitance there in series, meaning that's a basically current for high frequency currents that gives a lower impedance route to ground on that one. So it's limiting the output power or output power to the load for high frequencies. Yes, but it's done on output. That looks really funny for the dinosaur like me. I usually do that kind of limitations on the low signal part. But anyways, this is classical amplifier. I have been using those in some of the laboratory exercises actually 10 years back in Finland. Okay, that's another way how to get more power from lower power amplifiers. So this basically, if you have a you can do this one quite safely with, say, general purpose operational amplifier. So if you need, say, some watts of power, you know that the small signal amplifiers can provide only, say, 10 to 100 milliwatts of output power. Okay, but if you put a lot of those as voltage followers, you know, and short the input and output, which actually may end up having funny situations if you have a big biasing voltages or currents on those amplifiers. But say this works in most of the operational amplifiers. So if you need, say, few times more than single amplifier can supply, then you put those on open the followers, and then you can drive it like that. Okay. And yes, it doesn't show, but you should balance it by putting small resistors, so they are not short-circuited together, but rather when you have this amplifier, the voltage amplifier stage here, and then you have these voltage followers from the same signal, a lot of those. Don't do as it shows there, but you know, combine these outputs together with small ohmic, so small resistors, because otherwise you basically are running those amplifiers. Basically, if there's a small offset difference between the amplifiers, you're starting to have currents between the amplifiers. You don't want that one to happen. You want the amplifiers to add the currents together to have the bigger current output. Okay, but that's one way of doing it without transistors. Okay. Two amplifiers, AB class amplifiers. Ooh, that's a bridge configuration. So if you need more power to the load, you can always run amplifiers in a bridge, meaning you have signal gain of A on one end and signal gain of minus A on the other one, and then you have the load in between. That's a bridge amplifier connection. That's a neat trick if you want to actually double the maximum amplitude of the signal on a load, meaning quadruple the power without increasing the power supply voltage. Okay, that's how they do, for example, car stereo amplifiers. Car stereos, well, for historic reasons. Now there are all kind of inverters that you can use whatever voltage you need. But in historic reasons, the car stereos had that wonderful plus 12 volts power is there always, all the time. Okay. So how to get more than, more power from the car stereos if you are limited by that 12 volts all the time, without, having these switch power supplies to double the voltage or to make the power higher, or the voltage higher. And we have this minimum 4 ohm the loudspeaker. So if RL is 4 ohms, okay, and VCC only, a single-sided VCC is 12 volts. You don't get much of power out of that one, but if you can quadruple it, you start getting a nice, zoom, zoom, zoom on your car stereo. Yeah. You don't need subwoofers for that power yet. But if you quadruple it, then you can. Since actually this one runs, this part here runs the signal on positive amplification cycle. Well, let me take that one out. And this side actually on the negative side. So if you have plus minus VCC, it means that in between, okay, you have the voltage difference going from, if that is plus VCC, then we have 2 times VCC and minus 2 times VCC. Right. Compared to VCC and minus VCC. Doubled the output voltage, meaning 4 times more power, with the same power supply voltage. But of course now, okay, remember when we did the the AB class amplifier, that table. So now basically we are quadrupling the power load in out, power load power on load. We need to do also something for everything on the design. So but anyways, that's how it works. And there's a classic connection how you do it on operation amplifiers. By the way, this also works with, if you do a little bit of careful design, also with the single supply power. You just have then the reference ground is at the middle. But anyways, this is quite easy to make on single supply powers also. Yeah, just need this virtual ground somewhere. Okay. Yeah, maximum amplitude is now 2 times VCC, meaning 4 times. Quadrupling the power. Good. Yeah. Okay, and that's basically the okay. That's just a closer view of what we had there. So this amplifier has the output stage and then the amplification of one, and then the other one has the also the negative, and then you got the doubling this voltage. Good. And ooh, well, it still explains the same on positive cycle and negative cycle. Okay, and negative cycle. Yes. Hey. I'll just keep that one. It wasn't that nice, but okay. So the input current for the from by each power supply. Let's see, that's 2 times V0. Okay, yeah, the math is right. The two power supplies provide then in you know that's the amount 4 times VCC times V0 divided by pi divided by RL, and then the load has, well, actually the V0 squared divided by 2RL. That actually reminds me the same as the AB class amplifier efficiency. So if you are not, basically using the bridge amplifier design, it doesn't make anything for the efficiency. It just makes, you know, the requirement for the power source voltage lower. Okay, you get more power out of the design with the lower voltage. That's what it does. Okay. Yeah, that's more details. And then we have a summary table. Let me put those here. So, okay. Summary is exactly the same as class B, or class AB actually. Or the differences are just the power supply voltage. VCC for class B, but this bridge configuration, it's 2 VCC in principle. And then we have your class B. So efficiency is the same. It's just the matter of the matter of the output are all the power supply load. Good. All right, that's more or less summarizes the AB class amplifiers in total. There are some exercises what you should do by yourself. Should I actually mark those? Mark that list for them. Okay, good. Yes, so next week. Next week you have a lab, and after that you have this. Okay. Make sure you do the calculus yourself, since that's the only way you learn. Okay. Do it yourself. So, so basically there are, I think you know what are these referred to, so there are some exercises. So P5 and P3 and P5 are for thermal stuff, and then there are P6, P14, P18. So that's class A amplifier design. That's class AB. And then there's even some bridge with operational amplifiers. And then basically we still have a couple of extras here. P8, MP15, but those are extra. Meaning that if you do those, you will do fine on test. Good. So this is the. I would like to have a couple of words. Let me just first finish my recording. I will also send the recording again. Oh, there.